Okay, so last time we defined vectors and did some identities for them. This time we'll take a look at a couple of different ways of combining vectors, which we call products. We'll start with the scalar product, or as is more commonly called, the dot product. Now the dot product is defined, so you write A, nice little raised dot, B, and you read this as A dot B. It's defined to be the product of the x components, of the x components of the vectors plus the y components of the vectors plus the z components of the vectors. And there are several identities that we can have for this from this. So let's say this is my vector A, and that's my vector B, like so. Let's say the angle between the two is theta. And I will just go ahead and extend these lines for reasons that'll make sense in a moment. Okay, one of the first things that you can show is that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Now, if we think about this for a second, what is A cosine B? Well, A cosine B would be what you get, let's undo that, what you get if you project the vector A onto the vector B. We call that projection A parallel. And so we can say that it is that A dot B is also equal to A parallel times B, or by the same token, I could have chosen to project B onto A, giving a piece B parallel, and then we could also say that that's equal to A times B, parallel. So how we can interpret the dot product then is, in a certain sense, it is a measure of how parallel two vectors are. If we take a look a little more closely too, we can see that each of these sums is just a scalar multiplication, and scalar multiplication commutes. So in other words, A dot B, as a result, would have to be equal to B dotted with A. So the dot product commutes. This may seem obvious at the moment, but when we get to cross products, we'll see that the rules are a little different for them. And then we can also play with it a bit more, and we can show that if I dot A into the vector sum of B and C, that the dot product distributes over vector addition. So this is equal to A dot B plus, plus A dot C, like that. And if we take a look at this guy a little more, we can tease out the angle between the two if we need to. Star here will give me that the cosine of theta is equal to the dot product over the scalar product of the magnitudes. Now this comes really handy when you need to identify what are called the direction cosines of some vector. Direction cosines. So let's say this is my vector A, like so. The angle between the x-axis and A is usually denoted alpha. Between the y-axis and a is beta, and between the z-axis and a is gamma. So let's think a little more closely about what the cosine of alpha would have to be. Well, if we think back to our unit vectors, we know that the I hat unit vector points along the plus x direction. So I can get the direction cosine by dotting a with the unit vector and dividing by the magnitude of a times the magnitude of the unit vector. So let's see how that works. So this would be the cosine of alpha. So that would equal a dotted with I hat over a times the magnitude of I hat. We can follow that a little further. A dotted with I hat is ax comma ay comma az. We'll be dotting that with 1, 0, 0. And then, oops, just regular a there. We'll be dividing that by the magnitude of a, and then the length of the unit vector is 1 by definition. Well, if I do the dot product, this will be ax times 1 plus ay times 0 plus az times 0. So I'm just left with ax over a. So I get that the cosine of alpha is equal to ax over a. By the same token, I can also say that the cosine of beta is equal to ay over a, and that the cosine of gamma is equal to az over a. Excellent. Some other identities that we can come up with are that the square of the magnitude, so the square of the norm, if you think about it, you can get that from the Pythagorean theorem, and you should be able to convince yourself that that is going to work out to be a dot a. And a corollary of that gives us that I hat dot I hat equals j hat dot j hat equals k hat dot k hat equals 1. And if I dot, say, I with j, or I with k, or j with k, that I would get 0. Okay, and so what this also tells us then is if two vectors are parallel, the dot product will be a positive max. If they're anti-parallel, meaning they're pointing in the exact opposite direction, remember we saw that's cosine theta, so cosine of 180 is -1, so that will be a negative max. And if they're perpendicular, the cosine of 90 is 0. So there you go. Okay, let's just flesh out dot products here with just one quick little example. Let's say we need to construct we have partial knowledge of one vector and we desire it to be perpendicular to another one. So let's say the one we have partial knowledge of is I hat plus some unknown constant a that we're solving for. Actually, I should probably make my unknowns red, shouldn't I? There we go. And that will be times j hat. Well, then we'll say minus 3k hat. And we require that it be perpendicular to I hat plus j hat plus k hat. Now there'll only be one value of a for which this will work, so let's go ahead and find it. Well, what we can do is we can demand that they're dot products, so I hat plus a j hat minus 3 k hat dotted with I plus j plus k, we'll set that to 0. That's what the little circle over the equal sign means, is set equal to. Alright, so following this through, we can multiply them all together, and the only non-zero cross terms will be the ones where we have an I dot I, j dot j, k dot k, like so. So I dot I just gives me 1, aj dot j will give me a, and negative 3k dot k will give me negative 3. That's equal to 0. So that's only going to work if a is equal to 2. Excellent. Okay, there's also another type of vector product. This one actually gets called the vector product, or more commonly, the cross product. Its definition gets a little trickier. So A cross B, that's usually how you read it, is defined to be the x component is the product of AYBZ minus AZBY. Similarly, the y component is AZBX minus AXBZ, and the z component is AXBY minus AYBX. Now that's a mouthful to have to remember. Unfortunately, I do have sort of a cheater's mnemonic for it. If you write XYZ, XYZ twice like that, what you can do is to get the x component, you put a little arrow under the x there, and you look at the next two letters, and that tells you YZ. See, Y, Y, Z, Z. And then you minus and flip the subscripts. Then to get the y component, we move our little arrowhead over one and look at the next two letters, zx. So we have zx, then minus the reverse xz. Then finally, to get the z component, we put our little arrow under the z, look at the next two letters, xy. We have xy minus the reverse yx. So that's a way to remember it. In a little bit, I'll show you another way that's also really useful. One of the more surprising properties, possibly, of the cross product is that it anti-commutes. So what that means is that A cross B is not equal to B cross A, but it's actually equal to the negative of B cross A. In other words, the resultant vector points in the opposite direction when we change the order of the cross product. Now, the way you prove that is you just go ahead and gut it through. So we can look and say, well, A cross B is oops. We'll copy all of that. We'll try that again. Copy that. So there we go. So A cross B is all of that stuff. Now, one of the things that we can go ahead and do is we can observe that if I multiply this through by -1, that would be the same thing as if I reversed the order of the subtractions. So then this would give me AZ BY minus AYBZ, and so forth. Okay, But then if I look at that, I realize that scalar multiplication commutes. So that would be the same thing as minus byaz minus bzay, and two more similar components. I look at that and go, my God, that is minus b cross a, and that completes the proof. Okay, similarly, you can show that the cross product does distribute over vector addition. That's kind of handy. So that'll be a cross b plus a cross c. And again, the proof is similar, gutting it out by components. So if I do a cross b plus c, this would be ay times, I'd have to take the z component of the vector sum of b and c, but that's the same thing as just bz plus cz, like so. And then I would have to subtract and reverse the components, so az by plus cy, and then two more terms. Okay, now I can go ahead and distribute the scalar multiplication over scalar addition. That's no problem at all. So this becomes aybz plus aycz minus azby minus azcy, in two more terms. Now, I can group this here. I can look and say, okay, let's pull the terms of the b's together. So this will be aybz minus azby plus aycz minus azcy, in two more similar terms. Alrighty then, if I look at this and I recognize that this is, I can treat this as the adding two vectors, one of whose x components is this, and another of whose x components is that. So we'll go ahead and write it that way. So this becomes aybz minus azby in two similar terms, plus aycz minus azcy in two more similar terms. If I look at that and go, oh my God, that is a cross b, and that is a cross c, and that completes the proof. Okay, in a similar vein, you can show, but I will leave as an exercise for you, that if I take some scalars, say n, and multiply that by a cross b, I can distribute the scalar multiplication however I like. So, in other words, I can be na crossed with b, crossed with b, or that could be a crossed with n times b. Either way. You can also work out here that two parallel vectors are going to give a zero cross product. So for instance, I hat cross I hat will equal j hat cross j hat equals k hat cross k hat equals the null vector. And similarly, you can show, and keep in mind here, the order matters. I cross j equals k hat in cyclic permutations. So what do I mean by that? What I mean is, again, we can go back to the same idea here. I can write ijk like so. And so I hat cross j hat is k hat. j hat cross k hat is I hat, and k hat cross I hat is j hat. Now if you've got them in the reverse order, you'll get the negative of that. So this would also be equal to the negative, oops, this would also be equal to the negative of j hat cross I hat, for instance. Okay, that's all very handy. Can be a little tedious to remember, and so there's a trick you can do. The cross product turns out to be the same thing as the wedge product in 3 and 7 dimensions, and conveniently we're working in 3 here. So we can write A cross B as a fakey determinant. This obviously can't be a real determinant because I'm sticking unit vectors in the top row of a matrix here, but just go with it. This is a mnemonic. And then I put the components of the first vector in the second row, like so, and the components of the third vector, the second vector, sorry, into the third row, by, bz, like so. Okay, and this gives you the same thing. If you want to find your determinants by expanding minors, knock yourself out. But the way I learned how to do, and I do that for 4x4 and higher, but for 2x2 and 3x3, there's a handy trick for doing determinants called plowing the field. So whenever you go down and to the right, that's a positive contribution. Whenever you go down and to the left, that's a negative contribution. So for instance, to get the I hat pieces, you'll get I hat of a plus I hat times AYBZ and a minus I hat BYAZ, like so, or AZBY, take your pick, like so. So that's going down into the left like that. Similarly, I go down into the right, J hat AZBX, down to the left, minus J hat AXBZ, like so. And then down to the right, K hat AXBY, or if you want to think of it that way, is down to the right, knock yourself out, minus K hat AYBX. So that's the plow the field method for finding the determinant of a 3x3 or 2x2 matrix, for that matter. It does not work for 4x4 and higher, but kind of handy to keep in the back of your pocket somewhere. Okay, so we can do a quick example here. Let's find the cross product of 3, negative 1, 2 with 1, 2, 3, like so. Alrighty then. So I do my fakey determinant, I hat, j hat, k hat, 3 minus 1, 2, 1, 2, 3. And you can do it by whatever method floats your boat. I'll go ahead and plow the field. So to get the I hat pieces, I'll have a plus negative 1 times 3. So negative 3 there. And then the negative contribution will be minus 2 times 2 is 4. So negative 4 I hat. Then for the j hat piece here, I will have a plus 2 times 1 minus, oops, yeah, plus, oh, my bad, a plus 2 times 3 is 6. Sorry about that. Minus, I'm sorry, no, I was right the first time, 2. My apologies there. So j hat, plow like this. In fact, I'll mark off how I'm plowing, like so. So j hat times 2 times 1 gives me 2. And then similarly, when I plow the other way, and this will be negative contribution, so I'll mark it in red, This will be doggone it. Try that again. That'll be minus 3 times 3 is 9. Okay. And then, there we go. And then finally for the last piece, the k-hat piece, we get 3 times 2 is 6 minus a negative 1 times 1 is negative 1. Okay, so it's negative 7 plus 7, so we get negative 7i hat minus 7j hat plus 7k hat. And there's your answer. Okay, some other handy identities that you can show is the square of the magnitude of A cross B be equal to A squared B squared minus A dot B squared. And you can show that by playing with components. Now there's something really useful here. If we go back to our identities with dot products, so going back to here, we know that A dot B is AB cosine theta. So A dot B squared would be A squared B squared cosine squared theta. So we'll have a 1 minus cosine squared, which gives us a sine squared. So that allows us to conclude that the magnitude of A cross B would be equal to the magnitude of A times the magnitude of B times the sine of the angle theta between the vectors. So if that's my vector B, and that's my vector A, that's my angle theta between them. If I go ahead and extend out the parallelogram like so, we can interpret the magnitude of the cross product as being the area of the parallelogram. Now to get the direction, if you play with the components of this, for this particular case you can work out, we know that it's got to be perpendicular both to A and to B from before, and you can work out in this particular case that A cross B is going to point up like so. And in general, you can get this by the right-hand rule, which I know you've seen before, but as a quick refresher, pardon me while I draw a very hideous right hand. So this is your thumb pointing straight up, that's your index finger pointing straight out, and these are the rest of your fingers pointing toward your palm at right angles to the other two fingers. So what you do is you put the first vector of the cross product on the index finger, so that would be the direction of A. The direction of B would be going into the page. Let me try to do a little better job of drawing that. Be going into the page like so, and so then A cross B would sit on your thumb like so. So you should take a moment to convince yourself that that's how that works. Another way you can do it, if it helps you to think about it, is you can think about the cap on a pop bottle, and if you twist it from A to B through the smaller angle, in other words the angle that's less than 180 degrees, the resultant vector, the direction that the pop that the lid moves is the direction that the cross product points. That's another way that you can think about it. Okay, so let's just do a quick example here with torques. So let's say we got ourselves a gyroscope, like so. And this will be a big honkin' gyroscope. In fact, we'll have the center of mass located 2 meters out from where the support is. Okay, so if we plot out the forces here, we will have a force of gravity pointing down like so. There'll be some sort of reaction force pointing up. So let's say the force of gravity works out to be 10 newtons down. The reaction force by Newton's second law, this is a static situation, would have to point 10 newtons up. Okay, so if we remember our definition of torque, the torque N is equal to R cross F. And yes, I know in many books you use tau, but in a lot of upper division physics texts they switch to N, so that's just a new one to get used to. Anyway, R is the position vector, so for instance here, let's say we want to evaluate the torques about the support right there, so that's where my axis will be. That means if I want to find the torque due to the reaction force, that would be the position of the reaction force crossed with the reaction force R itself. Okay, well in that particular case, it's going to be the null vector crossed with R because the reaction force is being applied at the axis we care about. And the null vector crossed with anything is just the null vector. So we get no torque about the rotation axis due to the support axis itself. Now the torque due to gravity, that will be a different kettle of fish. So that will be the torque due to gravity will be equal to the position vector for the point of application for the force of gravity. There it is, crossed with the force of gravity itself. Okay, so this will be Rg cross Fg, like so. Alright, so if we do this by components, see that Rg would be located at 2, 0, 0 meters. And we'll be crossing that with the force of gravity, which will be 0, 10 0 newtons. Okay, the way you handle the units is to just multiply them, so that's all fine. So we're left with my torque being equal to, well, we can do IJK 2, 0, 0, 0, 10, 0, I'm sorry, not 10, minus 10, because we're pointing down, 0, negative 10, 0, Newton meters. All right. Well, if we go and start plowing the field, let's take a look at the eyepieces here. Nothing, nothing, zeros in both cases. We can go ahead and do this again for the J pieces. 0 and a 0 because we pick up zeros in both cases. So that doesn't contribute either. And then finally, we can do the K piece. Alright, so we've got that guy there, negative 20, and that guy there, 0. So the answer is -20 Newton meters in the k-hat direction. So that means that the torque N is pointing into the page. And you should convince yourself of that by the right-hand rule. Go ahead, make your hand into that shape. Point the index finger on the position vector. Point your middle finger on the force of gravity. Your thumb should be pointing into the screen when you're looking at this. Okay, there are a couple of other identities that we have when we're playing with these dot and cross products, and we call them collectively the triple products. And there are two different ones. There's the scalar triple product, and that is A dotted into B cross C. So the way you can interpret this is if that's B and that's C, we know that B cross C will point straight up perpendicular to both of them. Now if this is my A, like so, this would correspond to multiplying the projection B cross C onto A, or the projection of A onto B cross C. But either way you care to think about it, that amounts to being equal to, and forgive the horrendous art that you're about to have here, the volume of that. It's supposed to be a parallelepiped, and I'm really sorry it didn't come out like that, but that's what it's supposed to be. Okay, there is an identity for this, and that is that A dot B cross C is equal to A cross B dot C, which shouldn't be too surprising, since either way we should be getting the volume of a parallelepiped. Now, a way to think about this is when I dot A into that B cross C, that would be the same difference as if when I go to this mnemonic here, if I were to just put the x, y, and z components of the thing I'm dotting into the top row, you can convince yourself that that's true. So this would be ax, bx, oops, my bad. Try that again. ax, ay, az, and then I have my bx, by, bz, cx, cy, cz, like so. Now to get this A cross B dot C would be the same difference as C dot A cross B, because the dot product commutes. Now I can't flip the order of the A cross B. That won't go. So I need to get this into some sort of form where I've got the C's in the top row, and then the A's and B's in the bottom row of my determinant. Alrighty. Well, let's think about how to do that. You remember that when you're taking the determinant, if you swap two rows, so let's say I swap the third and the second row here so that I'll temporarily have the C's in the middle and the B's at the bottom, that would be the negative of that. So that first one's going to give me a negative. And so I'll put some parentheses around it because we'll need to think about the next step. There we go. And then the next step will involve me swapping. I now have the b's in the bottom where they're supposed to be, but I've got the a's and c's reversed, so I'll need to swap it again like so. So I pick up another minus sign. The two minus signs cancel, and that completes the proof. All right, so that is the scalar triple product. Another one that you'll run into when we get into rigid rotations is the vector triple product. Okay, this one is A cross B cross C, like so. Now, it turns out that the vector triple product does not associate, so it's not equal to A cross B cross C. So it's different there. But there's a handy way to remember this if you write some scalar multiplications a little funny. It's B times A dot C minus C times A dot B. This usually gets called the back cab rule because it's back minus cab. So that's at least a little bit helpful there. Okay, so that's our treatment of vector products. In the next video, we will go into working on coordinate transformations.